Today we will analyze the effect of air resistance on a stack of coffee filters that is moving through the air. I am joined today by Giselle and by Isabel. Thank you very much. Here is a stack of coffee filters. I'm going to drop these filters above a motion detector, which is connected to a LabQuest. This will allow me to measure the position and velocity of the stack of filters as it moves through the air. Let's start our measurement now. Now let's analyze our data.
Let's look at a graph of position versus time. Here I am plotting position on the vertical axis and time on the horizontal axis. Here's what we get. The position starts at 0 and it increases as time increases. The slope of the line begins at 0 and the slope increases, and eventually, after about 0.9 seconds, it reaches a constant value of slope. If this was a case of constant acceleration, we could apply the kinematic equations. This is what we would get. We started at a velocity of 0, so the position x is given by a half gt squared, where g is the acceleration due to gravity. Let's plot that on these axes. The red curve is the theoretical curve, 1/2 gt squared. You can see that the position which was measured is less than the theoretical value. This suggests that our acceleration is something less than g. It is less than 9.8 meters per second squared. Now let's look at the velocity. Here we plot velocity on the vertical axis versus time on the horizontal axis. Here's what we get. The velocity starts at 0 and it increases. The slope of the tangent to this graph is decreasing as time increases. It's high here, as you go along it gets lower and lower, and eventually it becomes 0. At this point we have constant velocity. If we applied the kinematic equations to this problem, and if we had constant acceleration, this is what we would get. V equals gt. Here's that plotted on these axes. The blue line is a graph of V equals gt. It has a constant slope. What we notice here is that for velocity versus time, the measured value, the slope is not constant. The slope is decreasing as time increases. Since the slope of the tangent is the acceleration, we conclude that the acceleration is decreasing as the object falls. Why does the acceleration decrease? Giselle, this is a question for you. Yes, you're right. It decreases because there are two forces involved. We have the force of gravity, but we also have another force called the drag force. Gravity acts down, but the drag force acts up. The drag force is a velocity-dependent force that opposes the motion of an object as it moves through a fluid such as air or water. Here's a free body diagram. This dot represents the coffee filter. There's a force of gravity acting downwards, Fg, and the drag force acts upwards, Fd. It acts opposite to the direction of motion, and it depends on the velocity. The acceleration is down, and let's apply Newton's second law to this problem. And we'll take the x-axis to be downwards positive. The net force is Fg minus Fd, and that equals mass times acceleration. At the start, v equals 0, and Fd is equal to 0. So this equation becomes Fg equals ma, or mg equals ma. And the solution is that A equals G equals 9.8 meters per second squared. But when V increases, Fd increases. And that is going to decrease the net force, which will decrease the acceleration. And eventually, the net force is going to be zero when the drag force equals the force of gravity. In that case, the acceleration is zero and v is a constant value. And that constant value of v at the end is called the terminal velocity. Here's a graph of velocity versus time for the coffee filter. As you can see, the acceleration or the slope of this graph is decreasing with time, and eventually the slope becomes zero. At this point we have zero acceleration and constant velocity. I took an average of these values of velocity and I got 1.51 meters per second for the terminal velocity. Causes of the drag force. There are two types of drag forces. One is called the inertial drag, and that's due to inertial forces. The moving object pushes away the fluid in front of it. This force depends on the mass of the fluid which is pushed away. And in this case, there is turbulent flow of fluid around the object. And an example of this would be a ball moving through the air. And then there is viscous drag. It is due to viscous forces. Viscous forces are between the fluid molecules and the surface of the moving object. There is laminar flow of fluid around the object when we have viscous drag. An example of this would be dust slowly sinking in a liquid. Reynolds number. In order to determine whether or not we have viscous drag or inertial drag, we need to look at the Reynolds number. The Reynolds number is a ratio of the inertial forces to the viscous forces. And it can be written as rho VL over eta, where rho is the density of the fluid, eta is the viscosity of the fluid, v is the speed of the object, and L is the size of the object, such as the diameter of the coffee filters. If the Reynolds number is high, greater than 1,000, we have inertial drag. If it is low, less than 1, then we have viscous drag. If it is between 1 and 1,000, then it may be a combination of the two. Let's look at the inertial drag force. We have inertial drag for high Reynolds numbers, greater than 1,000. We can write it like this. Fd equals 1/2 CD rho AV squared, where CD is a drag coefficient, and it depends on the object's shape. Rho is the density of the fluid, A is the cross-sectional area of the object, and V is the speed of the object. Note that the inertial drag force is proportional to the square of the speed. Let's look at the drag coefficient. CD. Here are the drag coefficients for different objects in order of increasing drag coefficient. For a dolphin we have 0.0036. Fighter aircraft, 0.016. 0.23 for a car. 0.5 for a sphere. A cylinder traveling lengthwise, like this, it's 0.8. And for a cylinder traveling sideways, like this, it is 1.1. Now let's look at viscous drag. We have viscous drag for low Reynolds numbers, less than 1. And we can write it like this. Fd equals Bv, where B is a constant which depends on the size and shape of the object and viscosity of the fluid, and V is the speed of the object. Note that for viscous drag, the drag force is proportional to the velocity, whereas it is proportional to velocity squared for inertial drag. For a spherical object of radius r moving in a fluid of viscosity eta, we can write the drag force like this. 6 pi eta RV. where r is the radius of the object. Let's calculate the Reynolds number for a few cases. The Reynolds number is rho VL over eta. Here's the density and viscosity for different fluids. For air, the density is 1.293. And for liquids such as water, olive oil, and honey, it is much higher, up to 1400 for the honey. For viscosity, for air, it is the lowest, 1.8325 times 10 to the negative 5. Then it is larger for the liquids, 1 times 10 to the negative 3 for water, up to 84 times 10 to the negative 3 for olive oil. Let's look at the case of air. Reynolds number could be written like this. We have the density of air, 1.293, times V times L, divided by the viscosity of air, 1.8325 times 10 to the negative 5. And this becomes 70559 times V times L. Note that when V increases and when L increases, we are more likely to have inertial drag. Let's look at our coffee filters. And we'll say V is 0.2 meters per second. And the L is 15 centimeters, or 0.15 meters. Let's put in the numbers. Reynolds number is 7055 times 0.2 times 0.15, and we get 2117. This is greater than 1,000. So this is inertial drag. Now let's consider a smaller object. Let's take a grain of pollen moving in air. We'll give it the same velocity as a coffee filter, 0.2 meters per second. The L now is the diameter of that grain of pollen, which is, for instance, 20 micrometers. Putting in the numbers, 70559 times 0.2 times 20 times 10 to the negative 6 gives us 0.28. This is less than 1. So this is a case of viscous drag. Note, we have a much smaller length for the pollen than we had for the coffee filter. So we had viscous drag for the pollen. This is a very exciting part of the presentation. We're going to look at pollen falling through air. We're going to find a differential equation, and then we're going to solve that differential equation. A grain of pollen of mass m starts at rest and falls through the air on a day with no wind. Determine the position, velocity, and acceleration as functions of time. Let's draw a free body diagram. The dot represents the grain of pollen. Force of gravity, Fg, is down. Drag force, Fd, is up. Acceleration is down. And the x-axis is positive going downwards. And let's start it at x equals 0. Let's write the differential equation. We'll apply Newton's second law to this free body diagram. We'll take down to be positive. So the net force is Fg minus Fd. Since the force, drag force is upwards, I put a negative sign in front of it. And that equals mass times acceleration. Now, the force of gravity is equal to mg. The drag force is equal to bv. This is pollen. It's very small, so it's going to be a viscous drag. And then the acceleration is dv by dt. So let's put these three things into our equation for Newton's second law, and this is what we get. This is our differential equation. mg minus bv equals m dv by dt. Now we need to solve this equation for v. How can we solve it? Yes, Isabel is correct. We solve it by separation of variables. Good answer. So here's our equation. And what we want to do is put all the v's on one side and all the t's on the other side. So here, we divide by mg minus vv, and we multiply by dt, and this is what we get. Now, the left side has the v's, the right side has the t's. So these variables are separated. Now we can integrate. This is what we get. I took the m outside of the integral since it is a constant. To solve this integral, well, the integral on the right is easy. It's just t. The integral on the left is a little bit more difficult. What we can do is a u substitution. Let's say u equals mg minus vv. Then we'll take the du. Since mg is a constant, du equals negative b dv. So let's solve this thing for dv. And we get this. dv is negative du over b. So now what we want to do is replace dv with negative dv over b. So make that replacement there. And instead of mg minus bv, we'll put u into our equation. So make those two replacements. And this is what we get. Negative m over b du by u equals dt. Now let's multiply through by negative b over m, and this is what we get. So now it's easy to solve this integral. Du over u is ln u. Integral of dt is t. So this is what we get. ln u equals negative b over mt plus c1, where c1 is a constant. So this is what we have. Now, we don't want ln u, we want u. So let's take e to both sides of the equation. So e to the ln u equals e to negative b over mt plus c1. This exponential function on the right can be written as two factors, like this. E to the c1 times e to negative b over mt. E to the c1 is just another constant, which I can call c2. And e to the ln u is just u. So this is what we get. U equals c2 e to negative b over mt, where c2 is a constant. Now let's put what u is. U is mg minus bv. So we get mg minus bv equals c2 times e to negative b over mt. Now we need to find that constant c2. So we need to determine it. How do we determine it? Yes, Giselle is correct. We need to find some initial condition. What do we know? What was the velocity at the initial, when t equals 0? The object started at rest. So we know that at t equals 0, v equals 0. This is our initial condition. Let's put these two things into this equation. This is what we get. mg minus b times 0 equals c2 e to negative b over m times 0. Well, this term is 0. This is e to the 0, which is 1. So we get mg equals c2. Now put the mg into our equation for c2, and then this is what we get. mg minus bv equals mg times e to negative b over mt. Now we need to solve this equation for v. So we can rearrange it like this. Then we could divide by v and then take out a common factor of mg over b. And this is what we get. Here's our solution. V equals mg over b times 1 minus e to negative b over mt. Let's see if this solution makes sense. Let's check it. So when t equals 0, or what does this solution give us? When t equals 0, this exponential function is e to the 0, which is 1. So we have 1 minus 1, which is 0. So when t equals 0, v equals 0. That's what we expected. We started at rest. Now let's look at when t goes to infinity. When t goes to infinity, the exponential function becomes e to the negative infinity, which is 0. So this is 1 minus 0. And so v is mg over b. That is a constant. It doesn't depend on time. And after a long time, we expect v to become a constant equal to the terminal velocity. So our equation makes sense. Here's what we got for the v. Now we want to find the acceleration. Well, acceleration is dv by dt. So we just have to differentiate this function. Let's do that. Take out the common factor mg over b right here. Derivative of 1 is 0. And then we have the negative. And then we differentiate e to negative b over mt. To do that, we could use the chain rule. Differentiate with respect to negative b over mt. That gives us this, e to negative b over mt. And then differentiate negative b over mt with respect to t, which gives us negative b over m. So now things here cancel out. We have the b cancels out over here. M cancels out. And we're left with just g. And so our solution becomes a equals g times e to negative b over mt. Let's check this solution. When t equals 0, this exponential function becomes e to the 0, which is 1. So a equals g. When t equals 0, the drag force is 0. The net force is mg, so ma equals mg, acceleration equals g. When t goes to infinity, this exponential function becomes e to the negative infinity, which is 0. So therefore a equals 0. And after a long time, we reach terminal velocity. Velocity is constant, so the acceleration must be 0. So our solution makes sense. Now let's calculate the position. v equals dx by dt, and it also equals this, mg over b times 1 minus e to negative b over mt. That's what we just calculated for the velocity. So we need to solve this differential equation, and again, we can use separation of variables. Multiply both sides by dt. This is what we get. So now we have x on the left side, t's on the right side, and we can integrate. This is what we get. So let's do that integration. So integral of dx is just x. Then integrate this first factor, 1 is just t. So mg over b times t. Then we have the constant negative mg over b, so negative mg over b, times negative m over b, times e to negative b over mt plus c. c is a constant. The result of an integral, if we differentiate the result of an integral, we must get what's inside the integral. So if we differentiate this, we must get this. If that is true, then this is the solution of the integral. Let's look at this. d e to negative b over mt by dt is negative b over m times e to negative b over mt. So each time we differentiate this exponential function, we get a factor of negative b over m coming in front. So we don't want this negative b over m in front, because we want just this. So that's why we multiplied by negative m over b. If we multiply by negative m over b, then the m's are going to cancel out, and the b's cancel out, and negative times a negative is positive, and so we get e to negative b over mt. So that's just a verification that this is the solution of this integral. Let's simplify it some more, and this is what we get. mg over b times t plus m squared g over b squared e to negative b over mt plus c. Now we need to find that constant c. What is the initial condition that we can use? What was the position when t equals 0? Correct, Isabel, good. When t equals 0, x equals 0. So let's put t equals 0 and x equals 0 into our equation here. And this is what we get. 0 equals mg over b times 0 plus m squared g over b squared e to the negative b over m0 plus c. Well, this term is 0. This exponential function is e to the 0, which is 1. And so c is negative m squared g over b squared. Now, put the c, this c, back into our equation, and we get our final answer. X equals negative m squared g over b squared plus mg over bt plus m squared g over b squared e to negative b over mt. That looks like a pretty complicated function. To understand this function, let's see what it is when t is close to 0 and when t is very large. So when we want to get the position near t equals 0, what we should do is do a Taylor expansion of this exponential function, e to negative b over mt, about t equals 0. So this was Taylor's formula, up to second order in t. F at t equals f at 0, plus t minus 0 f prime at 0, plus t minus 0 squared over 2 factorial f double prime at 0. F at t is this. When t equals 0, it is just 1, because e to the 0 is 1. F prime at t. When we differentiate this, we're going to get a factor of negative b over m coming in front. So we get negative b over m, e times e to the negative b over m times t. At t equals 0, this becomes e to the 0, which is 1, so we get negative b over m. Second derivative. When we differentiate again, we get another factor of negative b over m coming in front. So we have b squared over m squared times e to negative b over mt. When t equals 0, this becomes e to the 0, which is 1. So f double prime at 0 is b squared over m squared. So now, let's put these things into our expression. So 1 goes here. Negative b over m goes here. And b squared over m squared goes here. And this is what we get. E to negative b over mt is 1 minus b over mt plus b squared over 2m squared times t squared. So let's use this expansion near t equals 0 in our result for x. So there's our expansion. This is x. So now we're going to replace e to negative b over mt in red with this expansion. Make that replacement. And this is what we get. Now certain things are going to cancel out here. This term and the 1. Negative m squared g over b squared plus m squared g over v squared, that they sum to 0. So that cancels out. Also, this term, mg over b times t, is going to cancel out with this term, b over m, because m squared g over b squared times b over m is mg over b. So they cancel out. So this and this cancel out. And what are we left with? We're left with the final term. And look, the m squared cancels with this m squared. The v squared cancels with this v squared. And what we are left with? We are left with g over 2 times t squared. So this is what we get. Near t equals 0. X x equals 1/2 gt squared. This is same as position when there is no drag force. So when t equals 0, velocity is 0 and there's no drag force. So the acceleration is g, the acceleration due to gravity. And using the kinematic equations, the position would be 1/2 gt squared. So this is what we expect it to be. That's good. Now, let's look at the position at large times. At large times, when t becomes much larger than m over b, this exponential function becomes 0. And then, so then we get rid of this term goes away. And this is what we're left with. X equals negative m squared g over b squared plus mg over b times t. This is a linear function. The position is linear at large times. If we have a linear position function, then we will have a constant velocity, and that's what we expect it to be. At large times, we have a constant velocity. So this thing makes a lot of sense. The slope of the linear position function is what's in front of the t, mg over b. And this slope is the terminal velocity. So the terminal velocity is mg over b. The time constant. This is the acceleration, ge to negative b over mt. We can write that acceleration as ge to negative t over tau, where tau is called the time constant, and tau equals m over b. The time constant is measured in seconds. It has to be in seconds because the argument of the exponential function must be dimensionless. So t is in seconds, the tau must also be in seconds. Another way to see that, mass is in kilograms, b is in newtons per meters per second. And if you work that out, you'll find that it is in seconds. Let's see how acceleration changes when we increase the time by the time constant. When t equals 0, a equals g, because e to the 0 is 1. When t equals tau, a equals g times e to negative tau over tau. This is e to negative 1, which is 1 over e. So a equals g over e. When t equals 2 tau, a equals g times e to negative 2 tau over tau. This is e to negative 2, which is 1 over e squared. So we get g over e squared. Note, when we go from t equals 0 to tau, we've decreased the acceleration by the factor 1 over e. When we go from tau to 2 tau, we decrease the acceleration by the factor of 1 over e again. When the time is increased by tau, the acceleration is decreased by 1 over e. Let's plot the acceleration versus time. This is the equation that we are plotting. Acceleration on the vertical axis is written in terms of g. The time on the horizontal axis is written in terms of tau, the time constant. Here's what we get. It starts at g at t equals 0, and then it exponentially decreases to 0. And it's pretty much close to 0 after a time of 5 tau. So after a time of 5 tau, we can say that the system has reached steady state. Look at this factor e to negative t over tau. When t equals 0, it is 1. As t increases, it gets closer and closer to 0. When t equals 0, the acceleration is g. It is g away from the final value of a equals 0. When t equals tau, the acceleration is g over e. It is now g over e away from the final value of 0. When t equals 2 tau, the acceleration is g over e squared. It is now g over e squared away from the final value of a equals 0. When the time increases by tau, the acceleration gets closer to 0, by a factor of 1 over e. Velocity and time constant. This is the velocity. Using the time constant, we can write it like this. Vt times 1 minus e to the negative t over tau, where Vt is the terminal velocity. Tau is m over b, Vt is mg over b. Let's see how the velocity changes when we change the time by the time constant. When t equals 0, v equals 0. T equals 0, this is e to the 0, which is 1, so 1 minus 1 is 0. When t equals tau, v is Vt times 1 minus e to negative tau over tau. This is e to negative 1, which is 1 over e, so it becomes Vt minus Vt over e. Note, at t equals tau, it is Vt over e away from the terminal velocity. When t equals 2 tau, v is Vt times 1 minus e to negative 2 tau over tau. This is e to negative 2, or 1 over e squared. So it becomes Vt minus Vt over e squared. Note, at the time of 2 tau, it is Vt over e squared away from the final velocity of Vt. When the time is increased by tau, the velocity gets closer to Vt by a factor of 1 over e. Let's look at the graph of velocity versus time. Here we are plotting this function. Vertical axis is in terms of Vt, horizontal axis in terms of the time constant tau. Here's what we get. It starts at 0, and it increases. As it increases, the slope of the tangent line becomes smaller and smaller. That means the acceleration is becoming smaller. Eventually, the slope becomes equal to 0 over here, and it moves at constant velocity, the terminal velocity. So after a time of about 5 tau, it has reached the terminal velocity. Let's look at the factor 1 minus e to the negative t over tau. When t equals 0, it is 0. As t increases, it gets closer and closer to 1. When t equals 0, the v is Vt away from the final value of Vt. When t equals tau, v is Vt times 1 minus 1 over e, so it is Vt over e away from the final value of Vt. When t equals 2 tau, v is Vt times 1 minus 1 over e squared. It is now Vt over e squared away from the final value of Vt. When the time increases by tau, the velocity gets closer to Vt by a factor of 1 over e. Let's calculate the terminal velocity. At terminal velocity, the net force is 0. So here's the net force. Fg minus Fd equals 0, and we're using this free-body diagram. So Fd equals Fg when it is at terminal velocity. Now let's model the grain of pollen as a sphere of radius r equals 10 micrometers and a mass of m equals 5 times 10 to the negative 12 kilograms. So this is how we can write the drag force for viscous drag. 6 pi eta r Vt. So eta is the viscosity of air, and mg is the force of gravity. Let's solve this for Vt. Vt equals mg, or 6 pi eta r. Let's put in our numbers. Mass is 5 times 10 to the negative 12. G is 9.8. 6 pi, 1.8325 times 10 to the negative 5. That is the viscosity of air. And then the radius of the grain of pollen is 10 times 10 to the negative 6. And we get 0.014 meters per second. Note that this is much less than the value we measured for the coffee filter, which was 1.51 meters per second. The terminal velocity when we have viscous drag is much less than the terminal velocity when we have inertial drag. Let's look at the calculation of the time constant. For the same grain of pollen, radius is 10 micrometers, mass is 5 × 10⁻12 kilograms, and the VT, which we just calculated, 0.014 meters per second. At terminal velocity, the drag force equals the force of gravity because the net force is 0. For viscous drag, we can write the drag force as V times V. In this case, it's V times Vt, since it is moving at terminal velocity. Force of gravity is mg. The time constant, tau, is m over b. So we can get that from this expression. Just divide by bg. Divide each side by bg. And then you're going to see things canceling out. B cancels out here on the left. G cancels out there on the right. And so we get m over b equals vt over g. And so our tau becomes vt over g. And let's put in our values. 0.014 over 9.8 equals 0.0014 seconds. The time to reach terminal velocity is about 5 times the time constant. So delta t is 5 times tau, which is 5 times 0.0014, which is 0.0070 seconds. Compared to the time for the coffee filter to reach terminal velocity from our experiment, it was 0.8 seconds. The time constant for viscous drag is the time to reach terminal velocity for viscous drag is much less than the time for inertial drag, as demonstrated here. Here's a graph of position versus time. I'm writing the position in terms of m squared g over b squared, and the time is written in terms of tau, the time constant. Here's what we get. It starts at 0, the position increases, the slope also increases, and eventually the slope becomes constant, and the function becomes linear after a time of about 5 tau. Let's compare with electric circuits. The differential equations, solutions, and time constants are similar for viscous drag, LR circuits, and RC circuits. Here's what we just found out for viscous drag. This is our differential equation, and we solve for v as a function of time. M, g, and b are constants. And the time constant is tau equals m over b. For LR circuits, this is what we have. This is our differential equation. The current is I. We want I as a function of time. And E, R, and L are constants. Notice the similarities between these two equations. So they will have similar solutions. And the time constant is just L over R. So we took the coefficient of the derivative. So for viscous drag, we took the coefficient of dv by dt and divided by negative of the coefficient of v, so m over b. And for here, coefficient of dv by dt divided by the negative of the coefficient of I, so L over R. And also, we have the RC circuits. This is our equation. Now we want to find Q, charge, as a function of time. And E, C, and R are all constants. What do you think the time constant will be for the RC circuit? Isabel? That is incorrect. Giselle? Yes, you are correct. It is RC. Isabel said that it is R over C, but it is R divided by 1 over C, which gives us RC. It's all right, because Isabel is taking this class for the first time, and we haven't yet gotten to LR and RC circuits. That comes in the next semester. Whereas Giselle has actually taken this course 6 times. She really loves this class. This is now a very exciting part of the presentation. That's why we have the curtains. We just looked at a case where we had inertial drag. We just looked at a case where we had viscous drag. Now we have a large object falling through the air. What type of drag force would we have for a large object? Correct, Isabel. Good answer. It's going to be inertial drag. So a large object of mass m starts at rest and falls through the air on a day with no wind. Determine the position, velocity, and acceleration as functions of time. Here's our free body diagram. The dot represents the object, force of gravity downwards, Fg, drag force upwards, Fd, acceleration is down, and let's take the x-axis to be positive going down, and we'll start at x equals 0 when t equals 0. Let's find the differential equation. So first of all, the net force from this free body diagram, Fg minus Fd, and that equals ma. Fg is just mg, Fd is kv squared. This is inertial drag, so it is proportional to v squared. And a is dv by dt. Let's put these 3 things into our equation from Newton's second law, and this is what we get. This is our differential equation. mg minus kv squared equals m dv by dt. Note the difference between the case for viscous drag. For viscous drag, it was just v. Now for inertial drag, it is v squared. This becomes a harder problem to solve because we have v squared instead of v. How can we solve this problem? Of course, we need to use separation of variables. So here's our equation. So let's divide by mg minus kv squared, multiply by dt, and we get this. Now we have v's on the left side and t's on the right side, so we can integrate. Here's what we get, taking the m out of the integral since m is constant. Now, before, when we had viscous drag, this was just a v here, not v squared. And then we could use a u substitution. And it was going to be ln u was the answer. But now it's more complicated to solve this integral. So let's rewrite it like this. Let's divide by the left side. Let's divide the numerator and denominator on the left side by k, like this. So m divided by k, mg divided by k, and k divided by k. So we get this, m over k times this. And now, let's say that this factor here is a squared. So a squared is mg over k, and therefore a is square root mg over k. This integral on the right is very easy to solve. It's just t. This one on the left, we can use, one way is to use trigonometric substitution. I can write it like this, by the way. I multiply by negative k over m, so I get negative k over m here. Here I have v squared over a. Up here was a squared minus v squared. But I multiply by negative 1, so now it's v squared minus a squared. So as I said, we could use trigonometric substitution to solve this problem, this integral. Or we could use the method of partial fractions. Both ways work. Today I will show the method of partial fractions since I think it's more straightforward. So we can write this. 1 over v squared minus a squared equals b over v minus a plus d over v plus a. b and d are constants which we need to find. On the right side, let's get a common denominator, which is v minus a times v plus a. So we get b times v plus a plus d times v minus a. for the numerator. V minus a times v plus a is just v squared minus a squared. So the numerators of this and this must be equal to each other. So we have this. V times v plus a plus d times v minus a equals 1. We have to solve this equation for the constants v and d. There's two methods to do this. Let's look at method 1. Let's find all the terms that contain v in them. So on the left side we have bv plus dv, and on the right side there's no v, so it's 0v. So we get this equation, v plus d equals 0. Now let's look at all the constant terms. On the left side we have ba plus d times negative a, and on the right side we have 1. So we get ba minus da equals 1. So we need to solve these two equations for b and d as functions of a. From the first equation you get v equals negative d. So put this into here, and we get negative dA minus dA equals 1, or d is negative 1 over 2a. And since v equals negative d, we get v equals 1 over 2a. So now we've got the two constants. Let's look at method 2. This equation is true for all values of v. It is true for v equals a. So let's put v equals a into this equation. Here we get v times a plus d times a minus a. This is just 0. That's why I chose v equals a. So we get b times 2a from here plus 0 equals 1. So b2a equals 1. Therefore b is 1 over 2a. Now let's put b equals negative a. First term here is going to be 0. Negative a plus a is 0. That's why I chose v equals negative a. Second term is d times negative a minus a equals 1. So d times negative 2a equals 1. d equals negative 1 over 2a. So now our integral becomes this. And this is easy to solve. This is ln v minus a. This is ln v plus a. So here's what we get for our integral equation. And let's multiply by 2a and then solve the integral. So we get here ln v minus a minus ln v plus a minus 2a k over m times t plus c1, where c1 is a constant. Note, when we do the ln function, we're taking absolute values. That will become important later. Let's simplify some more. ln v minus a over v plus a equals negative 2 square root kg over mt plus c1. And we want to get rid of the ln, so we take e to the ln, and e to the negative 2 times this. This exponential function on the right can be written as two factors, e to the c1 and e to the negative 2 square root kg over m times t. And this, when we take e to the ln, we just get v minus a over v plus a, and so it equals c2 times e to the negative 2 square root kg over m times t. Now we have to take care of this absolute value function. To do that, we need to consider the terminal velocity. When we have a large object falling through the air, the terminal velocity is the maximum velocity. So when v equals vt, the net force is going to be 0. So Fd equals Fg. Fd is kv squared for a large object. It's inertial drag. And when v is vt, Fd is kvt squared. So kvt squared equals mg. Solve for vt. Vt is square root mg over k. We just saw this. Square root mg over k. Square root mg over k is the a in our equation. So the velocity is always less than or equal to vt. So velocity is always less than or equal to a. So therefore, when we do this absolute value, v minus a is going to be negative or 0. So when we take the absolute value, we need to reverse it. It becomes a minus v, because a minus v is positive. So we get a minus v over v plus a equals c2 times the exponential function. Here's what we have. Now we need to determine the constant c2. So we need a condition. What is our initial condition for velocity? At t equals 0, v equals 0. So let's put these two things into this equation here. This is what we get. A minus 0 over 0 plus a equals c2 times e to negative 2 square root kg over m times 0. This is just a over a, which is 1. This is e to the 0, which is 1. So we get c1 equals c2. So we'll put 1 into our expression there for c2, and we get this. A minus v over v plus a equals e to the negative 2 square root kg over m times t. Here's what we have. Now let's solve for v. Multiply by v plus a, like this. Then find all the terms that contain v and put them on one side of the equation. And all the terms that do not contain v, put them on the other side of the equation, and we get this. So now divide by this factor, and we get this. So this is our velocity. Square root mg over k. This is the terminal velocity. Times 1 minus e to the negative 2 square root kg over mt over 1 plus e to the negative 2 square root kg over mt. Let's check this solution. When t equals 0, these exponential functions become e to the 0, which is just 1. So this is a 1 and this is 1. So we get 1 minus 1 over 1 plus 1, which is just 0. So when t equals 0, v equals 0, as expected. When t goes to infinity, now these exponential functions become e to the negative infinity, which is just 0. So what's in parenthesis becomes 1 over 1, which is 1. So v equals square root mg over k. It equals the terminal velocity. It is a constant. That is what we expected. This looks like a good solution. Now we need to calculate the acceleration. This is v. Acceleration is dv by dt. Here we have a quotient, a function in the numerator and a function in the denominator. We could use the quotient rule. d by dt of f over g equals f prime g minus fg prime over g squared. So let's apply the quotient rule to this function. First of all, we got the constant coming out in front, square root mg over k, square root mg over k. Then here we squared the g. So this is the g, and we squared it and put it here. Now, here, this is df by dt. So derivative of this, derivative of 1 is 0, and derivative of this, we have the negative, and then we got negative 2 square root kg over m coming in front when we take the derivative of the exponential function. So that's f prime. And then this is g, right here. They're the same. Then minus f, so this f is over here. Then we got here, this is g prime. The derivative of 1 is 0. Derivative of the exponential is this. We get the factor negative 2 square root kg over m coming in front. So that is what we get by applying the quotient rule. Now let's simplify further. this factor, 2 square root kg over m times square root mg over k, is 2g. And then some things cancel out. Let's look at what cancels out. Negative times a negative times a positive. That's a positive. Negative times a negative times a negative is a negative. So this cancels out with this. And then we are left with the ones. And this first one is going to be a positive, because negative times negative is positive. Second one is also positive, because we have negative times a negative. And so we get a factor of 2. 1 plus 1 is 2. And so we get a 2 times e to negative 2 square root kg over m times t. And then bring the 2 out in front, and finally this is what we get. A equals 4g times e to negative 2 square root kg over m times t over 1 plus e to negative 2 square root kg over m times t squared. Let's check this solution. When t equals 0, the exponential functions are equal to 1. So we get 1 over 1 plus 1 squared. So 4g times 1 over 1 plus 1 squared. 1 plus 1 squared is 4, so we get g. That's what we expect. When t equals 0, a equals g. At t equals 0, the drag force is 0 because velocity is 0. So we only have force of gravity acting. So a equals g. Now when t goes to infinity, these exponential functions become e to the negative infinity, which is 0. So we have 0 over 1 plus 0 squared, which is 0. So a equals 0. As expected, after a long time, the velocity is constant. The velocity is the terminal velocity, so unchangeable velocity means acceleration is 0. This solution makes sense. Now let's calculate the position. So here's our expression for velocity. And that equals dx by dt. So this is our differential equation. Let's separate variables and then integrate. So I multiply by dt and then integrate it. So we have this integral on the left, which is very easy. It's just x. And then we have this more complicated integral on the right. Let's look at that complicated integral. Let's consider it to be two separate integrals from each of these two terms in the numerator. So we have this integral and this integral. This integral can be easily done. We can do a u substitution. If u equals this in the denominator, then du is proportional to this in the numerator. So a u substitution will work. We would have integral of du over u, which is ln u. This one, we need to put it into this form. To do that, we multiply by e to the 2 square root kg over m times t. This is what we get. So we multiply through by this. So this is what we get in the numerator. Denominator becomes this. E to the 2 square root kg over m times t plus 1. So this now is in a form where we could do a u substitution. If u equals what's in the denominator, then du would be proportional to what's in the numerator. And this would again be integral of du over u, which is ln u. So now these integrals can be solved. So here's, I've written now in terms of the two things, this one and this one. Let's do this u substitution for the one in blue. That's u, this is du. For the red one, let's do w. This is w, this is dw. Put these into the integrals and we get this. We have an integral of dw over w, integral of du over u. Well, this is just ln w. This one is ln u plus a constant c3. And then we could combine these two ln functions gives us ln wu. Okay, so this is what we got for this integral. And w is this, u is this. Let's multiply them together. When we multiply w times u, we get this. And so now, this is back, let's go back to our integral equation. This is what it was. Now what do we have? We just found that this integral here is equal to this whole thing here. So let's put that into there. And integral of dx is just x. So this is what we get. We have the constant mg over square root mg over k plus then this constant here, 1/2 square root m over kg. That's right here. And then with the ln function, then plus another constant c4. C4 is a constant. Now, so that's what we have for position. We need to determine the constant C4. So what is our initial condition? At t equals 0, x equals 0. Put these into our expression, and we get this. 0 equals m over 2k ln e to the 0 plus e to the negative 0 plus 2 plus c4. This becomes, this is 1 plus 1 plus 2, so we get m over 2k ln 4 plus c4 equals 0. So c4 equals negative m over 2k ln 4. So put our c4 into here, and we get our final result. Drum roll, please. X equals m over 2k ln e to the 2 square root kg over mt plus e to the negative 2 square root kg over m times t plus 2 minus m over 2k ln 4. This is a very complicated function. Let's see what it is near t equals 0 and what it is for large values of t to help us understand it more. Position near t equals 0. So let's do a Taylor expansion about t equals 0 of this function. ft equals ln e to the gt plus e to the negative gt plus 2, where g is this. 2 times square root kg over m. This is the expression for the Taylor expansion. F at t is f at 0 plus t minus 0 f prime at 0 plus t minus 0 squared over 2 factorial f double prime at 0 to second order in t. Now, for our function here, f at 0 is ln 4, because this is 1 plus 1 plus 2 is 4. For f prime at 0, we get this. Now, I'm not going to work that out. I'll let the viewers, you viewers can work it out for yourself. F prime at 0 equals 0. And f double prime at 0 is 1/2 g squared. Isabel would like me to work out that thing in more detail. I'd like to do that, Isabel, but yes, Giselle. Giselle said it is very tedious. That's true, Isabel. It is kind of tedious, and this presentation is getting very long. Actually, this is the longest presentation we've ever done. I don't know how many viewers are still with us at this point. But I think if I go through this, it's going to be so tedious, and I'm going to lose even more viewers. So I'll tell you what. Let's do that. Okay, I'll tell you what. Why don't you try it on your own first? It's always good to try things on your own first to make sure you really understand it. And if you run into difficulties, let's get together and work it through together, okay? Okay, that's great. So I think we won't lose so many viewers if we do it this way. So f double prime of 0 is 1/2 g squared. Now let's put these things into our expression. So ln 4 is f0. 0 is f prime at 0. Half g squared is f double prime at 0. Make those changes. This is what we get. ln 4 plus t minus 0 times 0 plus t minus 0 squared over 2 factorial times 1 half g squared. So this term is just 0. For this term, let's square g, 2 kg over m. And then we get this. I'm sorry, g squared is 4 kg over m. So that 4 cancels out with the 2 times 2. And we get this, ln 4 plus kg over m times t squared. Now, here's our expression for x. So this ln function in red is what we just expanded with our Taylor expansion. So let's put what we just found out. Near t equals 0, it is this. Now, some things cancel out. This term, m over 2k ln 4, cancels out with this, m over 2k ln 4. So we are left with x equals 1 half gt squared. Same as position when there is no drag force. When there's no drag force, acceleration is just g. And from the kinematic equation, we get x is 1 half gt squared. This complicated function looks very simple when we make that expansion near t equals 0. Now let's look at what happens at large times. So here's our function. Now we want for large values of t. This term is e to the negative infinity, which is just 0. So this term we can cancel out. And then this term is very large, much larger than the 2. So the 2 we can just cancel out. And so this is what we have. When t goes to infinity, x is m over 2k ln e to the 2 square root kg over m times t minus m over 2k ln 4. Now, ln is the inverse of the exponential function. So this thing, once we work that out, it's just going to equal 2 square root kg over mt. And so this is what we get. M over 2k, these things here, plus 2 square root kg over mt minus m over 2k ln 4. Let's simplify this, and we finally get this. X equals square root mg over k times t minus m over 2k ln 4. So, at large times, the position is linear. So linear position means, take that derivative, you get a constant velocity, which is what we expect at large times. It's moving at the constant terminal velocity. And the coefficient of t is the terminal velocity. So the terminal velocity is square root mg over k. Let's look at the time constant for inertial drag. The time constant is this. We can write, this is our expression for acceleration. Now put in this, tau equals 1 half square root m over kg into this expression. And we get this. 4g times e to the negative t over tau times 1 plus e to the negative t over tau squared. Velocity. This is the velocity. Now put in the time constant. This is what we get. Vt, that's terminal velocity, square root mg over k is terminal velocity, times 1 minus e to the negative t over tau, over 1 plus e to the negative t over tau. And now the position. This is our position function. Let's put in tau. This is what we get. M over 2k ln e to the t over tau, plus e to the negative t over tau, plus 2, minus m over 2k ln 4. The time constants for inertial and viscous drag are different. For inertial drag, when the time increases by tau, the acceleration does not always get closer to 0 by a factor of 1 over e. And the velocity does not always get closer to vt by a factor of 1 over e. But after a long time, such as 9 tau, they do get closer by the factor of 1 over e, when the time increases by tau. Now, something very exciting is about to happen. Please pay close attention. This is so exciting. It's the most exciting part of the presentation. We are looking at the graphs for inertial drag. Here we are graphing acceleration on the vertical axis in terms of g versus time on the horizontal axis in terms of tau, the time constant. This is what we get. When t equals 0, the acceleration was equal to g. It starts with a slope of 0, and it decreases as time increases. Initially, it is concave down. Then it becomes concave up, and it falls to 0. After a time of about 7 tau, it has reached steady state. Note that for viscous drag, it reached steady state after a time of 5 tau. Also, when t equals 0, a is g. When t is tau, a is 0.78 g. If it decreased by a factor of 1 over e in the time tau, it would be 0.37 g. At time of 2 tau, a is at 0.42 g. If it was decreasing at 1 over e each time the time increases by the time constant, it would be at 0.14 g. So when time increases by tau, the acceleration does not always get closer to 0 by a factor of 1 over e. But it does when we're at very high times, such as times greater than 9 tau. Now let's look at velocity for inertial drag. Here I plot velocity in terms of the terminal velocity vt on the vertical axis. We have time in terms of tau on the horizontal axis. Let's see what we get. Velocity starts at 0, and it increases. As it increases, the slope of the tangent to the curve decreases, meaning the acceleration is decreasing. Eventually, the slope becomes 0, and the velocity reaches the terminal velocity vt, and that happens at about a time of 7 tau, whereas it was at 5 tau for the viscous drag. When t equals 0, v equals 0. It is vt away from the final value of vt. When t equals tau, it is at 0.46 vt. If it was getting closer to the final value vt by a factor of 1 over e, it would be at 0.63 vt. When t equals 2 tau, it is at 0.76 vt. If it was getting closer to vt by the factor of 1 over e, each time we change the time by tau, it would be at 0.86 vt. So, when the time increases by tau, the velocity does not always get closer to vt by a factor of 1 over e. That only happens for large times greater than 9 tau. Now let's look at position versus time. Here is position on the vertical axis in terms of m over k. Time on the horizontal axis is in terms of tau. Here's what we get. Position is 0 at t equals 0. Initially, it is proportional to t squared. Then at the end, it is has a constant slope. When greater than 7 tau, it is a constant slope. Let's see how we can measure the drag coefficient for our falling coffee filters. The falling coffee filters had inertial drag. In that case, the drag force was kv squared. And we can write the inertial drag force as 1/2 CD rho AV squared, where CD is the drag coefficient, rho is the density of air, and A is the cross-sectional area of the coffee filter. From this, we can write K. K is 1/2 CD rho A. Terminal velocity. Vt is square root mg over K. So what we should do then is, this is our K, that's our K, so put it into here. And this is what we get. Square root mg over 1/2 CD rho A. Let's solve this for CD. Let's square it and solve for CD. This is what we get. CD equals 2mg over rho A Vt squared. For the coffee filter, m was 0.00175 kilograms. Vt, as we measured, was 1.51 meters per second. Density of air is 1.293 kilograms per meters cubed. And the radius of the cross-sectional area of the coffee filter was 0.075 meters. Okay, so let's put those numbers into this expression. 2 times the mass, 0.00175, times G, 9.8, over density of air, 1.293, times pi, times r squared. So pi r squared is the cross-sectional area, times 1.51, Vt squared. And this is what we get, 0.66. Do you think this makes sense? Yes. Yes, Giselle, I think you are correct. It makes sense. Because for a sphere, CD was 0.5. And for a cylinder moving along its length, moving in the lengthwise direction, it was 0.8. And I think it's a good model of the coffee filter to be somewhere between the sphere and the cylinder moving lengthwise. So between 0.5 and 0.8, it makes sense. So I think 0.66 is a good answer. Okay, let's continue. Here's a summary of what we've learned today. First of all, we looked at drag force. There are 2 types of drag forces. One is viscous drag, where the force is proportional to velocity. Fd equals Vv. Then we had inertial drag, where the force is proportional to the velocity squared. Fd equals kv squared. The Reynolds number is the ratio of the inertial forces to the viscous forces. And from the Reynolds number, we can determine what type of drag force we have. We have inertial drag for high Re, greater than 1,000. And we have viscous drag for low Re, less than 1. Terminal velocity. When an object is dropped at rest in the fluid, the velocity increases, causing an increase in the drag force and a decrease in the acceleration. So we have the force of gravity down, the drag force up. The net force is Fg minus Fd. As velocity increases, Fd increases, causing the net force to decrease and the acceleration to decrease. Eventually, the drag force equals the force of gravity, and the acceleration is 0, because the net force is 0. And when that happens, the object moves at constant velocity, and that maximum constant velocity is called the terminal velocity, Vt. And here's our graph of velocity versus time for the coffee filter, and it reached a maximum final velocity of 1.51 meters per second. That's the terminal velocity. And from the terminal velocity, we were able to measure the drag coefficient of the coffee filter using this expression. And putting in the values, we got CD of 0.66 for the coffee filter. Differential equations. For an object dropped from rest in air, the differential equations for both types of drag forces were derived. For viscous drag, we got this. For inertial drag, we got this. The difference is this. We had a V here, we have a V squared here. And we solved those differential equations to obtain position, velocity, and acceleration as functions of time. The theoretical curves for position and velocity as functions of time matched the measured curves for a coffee filter falling in air. For both types of drag forces, the position is a quadratic function of time near t equals 0, and it becomes linear for large t. Time constant for viscous drag. For viscous drag, the time constant is tau equals m over b. And here's a plot of acceleration versus time. And we saw that when the time increases by tau, the acceleration gets closer to 0 by a factor of 1 over e. And we can assume that the system reaches steady state after a time of 5 tau, right here. Time constant for inertial drag. For inertial drag, the time constant is tau equals 1/2 square root m over kg. Here's our plot of acceleration for inertial drag. When the time increases by tau, the acceleration does not always get closer to 0 by a factor of 1 over e. That only happens for large times greater than 9 tau. We can assume that the system reaches steady state after a time of 7 tau, right here. Thank you very much for staying to the end of this very long presentation. Isabel, Giselle, and I really appreciate your viewing of our presentations, and we hope you come back again soon. Please be sure to like and subscribe. See you next time. Bye.